Hello everyone, welcome to my new YouTube channel, Wig Wizard. I am Hadi Musa, a PhD in electrical engineering. I created this channel to share basically my knowledge, experience, expertise in the field of electromagnetics. I'm going to discuss different electromagnetic related topics like antennas, antenna arrays, metasurfaces, RF passives, and similar things related to the industry, starting from the antenna and until the RF module, including the packages, tricks in the simulations, and basically the main goal is that to have these things as reference for myself in the future and for all of you guys who is interested. So my goal in this tutorial to basically design patch antenna with CST, very detailed tutorial showing hints and tricks in the software, how to understand it, if something happens wrong, how can we fix it. So this is the first goal. Second one is I provide some analysis or I discuss on whiteboard my thoughts, my tricks on how to design it, how to be fast in these designs. So in this example, I will do patch antenna designed for 10 gigahertz, fed with coaxial feeding mechanism. And my main goal is to understand the patch antenna design and getting familiar with the CST solver for such details of the model creation, setting out the simulations and so on, and to give hints on how to optimize the antenna design very quickly, what to expect, and so on. Well, let's do it then. So first I start to prepare the solver parameters, being ready for the range of frequency which I will be working with. Okay, so we can go to home units, we can check the dimensions. I will be working with gigahertz, and then the dimensions in millimeter, the time in nanoseconds, and also checking the simulation, deciding the frequency range. For example, let's say if I would target my center frequency around 10 gig, so I'll be working with, let's say, from 5 to 15 or something, like center frequency and a span of 5 gig in both ranges. Okay, so okay, and then from this tab basically we can decide the type of solver. So not from here, but we can go from home, deciding the solver frequency domain, and here we can actually go here if we have any excitation source or something, but yet we did not create any ports, and that's why we are not allowed to play with it. Okay, so now we are ready, like the grid is adjusted to our scale, our dimensions. So let's do it then. Okay, so I will start first creating the model, okay, the 3D model. So I start by doing squares. So I press the mouse and then escape, and then I get this window. I say, for example, I start with the ground. I will make it like square centered around the zero origin of this grid, and it will be the dimensions LG by LG. Okay, here we go. And then the elevation I'll start like E ground, and then the max is ground plus TG thickness. Okay, I'll choose the material like PC, and then press OK. Give me inputs like this. So first for now 10 millimeter, and the elevation will be 0 for me, and the thickness will be 0.05, for example. Okay, so now I created the ground. Okay, when we press shift and do with mouse, we make the rotations, and if we do control, we move in this way, and when we press both of them we press on the mouse, we move in this way. We can just drag it. So shift and mouse, we can rotate like this, and control we do like this, and press shift and control and pressing on the mouse, we can basically move in this way. Okay. So and here we scroll by the mouse. Okay. And if we also press on the scrolling and we move, we also do the same thing. Okay. And then I will do again the substrate by the same way, and then I'll use substrate. It's better always to use your things to be parameterized. Okay, so for example, it would be all in the same range. Of course, it can be different ways we can discuss later, about how to really plot in this way, but I prefer to be in this way such that later we can or you can always actually connect all parameters together in the way that when you change later anything, you change all of your problem. Okay, and then we'll start from E substrate until E substrate plus, let's say, H sub. Okay, and then we'll choose for now. Okay, I'll just get new material, and this new material, I'll call it sub 1, epsilon, sub. I would prefer to make it a little bit transparent so I can see through it. And I don't like this color, so I do like this. And then let's do this, okay? And then the values will be like 3 or something. Let's say 4.2 if we want to manage the FR4. We can actually pick up the material, but usually I prefer starting without loss, and then we can add the loss later. That's all. Okay. Okay, and then we'll do this, and then the elevation of the substrate we'll do from the ground, right after, like right above the ground. Okay, so start from here, and start. Let's say I'll start by 0.5 millimeter or something. Okay. Okay. Here's something like wrong a little bit about the shape which we created here, the ground. But let's see what we did. If we check the ground, we check here. Yeah, we find that we didn't do in the right way. Okay, like a little bit longer. So this is what I'm saying. So we can always do. And then actually I also want to add something just on the side if you're doing history parameters. And then you can actually access the steps you are doing. So you can also, for example, you can always go there to change something you can do here. And then, for example, if you change the name of the component here, you can say, for example, antenna, right? And then press OK, and then close, update. You can see that it's something like you created shape or something, like it follow the steps you did in the history, and then it works in this way. Okay, so we can access also here. We can say define component 1, right? So here command 1, we can say actually, yeah, so here this component, this is like antenna, right? But here like component 1, right? So we can, I mean, like this is the way how we want to change later. Okay, like if we do like this, and then okay, it does this way. You'll see this is some way how you can basically mimic this thing, like it's just give you way how to do it later. Okay, so I mean, like how if you want to change something later or something like this. Okay, so it's not anyway important. So okay, and then we want to create the patch itself. Okay, for the patch I prefer to do like this patch, and then everything will be centered. I choose it in this way, like it's up to your preferences, but for my preferences I like it this way. So I do like L patch X over 2, L patch X over 2, okay, and L patch Y over 2, L patch Y over 2, and then E patch then E patch plus TG, like the metal thicknesses, and then I'll pick up the PEC as well. Okay, and then let's do like this. Okay, I'll choose something like 5 mm for now, and the same, I'll make it like 6 so we can just observe the shape, you know, like not to be confused between X and Y just visually, but we will change it later when we design the antenna itself, the parameters. And then the elevation, we want it right after the substrate, right? The substrate plus substrate will give me like this, and here we go. Again, what's wrong here? Then go to the patch. Let's see what we did. So okay, here, yeah, I didn't do the dimension. Should be from negative to positive, so we are good to go now. Okay, so for now, it's like this is the antenna itself. If we press 1, by the way, it get me here directly. Press 1, just because they start to work with HFS, so the control thing is a bit different. Okay, so anyway, like again, this is shift, it rotates in plane. When I press control, it rotates the other way, and then when we press both, it drags. So we can just do the scrolling button and we do like this. Okay, so here we go. I mean, like now we plotted the patch. Okay, and then the second question is like how we want to feed it, right? And then how we want to decide the parameters. Okay, guys, now I will try to give my thoughts about like how to design the antenna, like dimensions, how to choose the substrate, at least the initial parameters, which we will start with on the CST, and then I will show how to use the solver itself to speed up and make the design of the antenna more systematic. So just similar to the dipole antenna, which is basically something like transmission line. This is what you find in books, I mean, like some transmission line, and it is open from here. And then we can start to split the arms, right? And then the field will be like this, and then the extreme case when we have the dipole. So the field lines will be like this, and the far field, this will connect, okay? And this is the radiated field. So we have a transmission line, the guided medium, and then we open it, and then the field like fringe in this way, and then it goes to the far field. So similar to this is the patch antenna, but just the mechanism a little bit different. So in the patch antenna, it starts generally like we have a metallic cavity. Okay, this cavity is like this and has some modes inside, like some field distribution depends on the dimensions, and decide the cutoff frequencies and so on. So if this is all metals and this is like, let's say, the ground, the patch, so it exists some modes. So in the case of opening the patches from the sides, like create them openings. So now we don't have walls anymore. So the fields which was there, okay, it exists, all of these things start to get out, right? And then in the far field, it do the same thing, right? So, and then by this way, it will be something like just the arrows will be something like this. And then will depend usually on the dimensions or something, but I'm just wanting to share that it is a cavity, it has some fields inside, and then it opens to the free space, right? So it means that finally what decides the resonance frequency or something is the cutoff frequency of any mode or something, which is proportional, like in the dominant modes we have just one cycle of the wave, so it's basically any dimension will be lambda over 2 of the frequency we want, and then the cutoff frequency will here. So for example, if we want to have cutoff to have the modes existing in frequency FC, I will calculate the lambda C, which will basically, I will adjust this edge to be the same length, and then I will have this mode propagating. So anyway, how to decide this lambda guide, so the wavelength. So this happens generally if like the problem will reduce actually to how to calculate epsilon effective, right? What does it mean? That if I have the patch like this and it exists in epsilon, the material like H, like the substrate, and then this metallic patch is relating to the far field, right? So what is the epsilon effective of this medium? So generally, if everything is so closed, like cavity like this, so if here is epsilon, it means that the solution there, it sees anything there, I draw metals or something, it sees epsilon. But here it's a little bit different. I see something definitely less than epsilon, because if there is a cavity here and all of it filled with this epsilon, is okay, I will get already epsilon. So we are expecting that it will be some value between 1 and epsilon, like r, just the relative one, okay? So how I will decide, generally we know that, for example, in the extreme case, when the substrate is so big, like I have something like this, infinite, so it's like I have here infinity length, and here's also infinity here, like, but here is free space, here is epsilon r, means that the value of epsilon effective is basically the average, right? And then it means that this value will be here in this case, epsilon effective equal epsilon r plus 1 over 2. And then when I shrink it more, I know that the fields are confined between this two pieces of metals and the fields are less there. So the value will be biased to the epsilon r. So we know that epsilon effective will be slightly smaller than epsilon r and bigger than epsilon r plus 1 over 2, and it's actually close to this, okay? So this what you will see generally in the online calculator things. You will see that epsilon usually, sorry, they start with, like they do analytically something like this, epsilon plus r over 2 plus, I'm not sure exactly, but maybe something like this, multiplied by something, this something proportional to h over w or something. Anyway, so when this h is higher, infinity, this one will vanish, and then I will have this value. When h is having something, this part basically contributes, and then it gives me the value of epsilon r. It's like very close to epsilon r. So it's like if you do like if you basically simplify it to be like epsilon r, okay, plus half minus something, this something over h over w like this, and w is the width of the patch antenna anyway. So this factor decides the confinement of the field. Like if the width is so high, it means the field is more confined. So for example, if I have the width is so high, the field is more confined, okay? And if the width is smaller, the field is usually fringing really easier. And then here it has more epsilon than this one, even if the height is the same, right? So this just generally give you how we think of it. So to summarize it, we have patch antenna, right? And we know that it represents something like a cavity that it is controlled by the dimension L1, for example, and L2. And we know that once L equal the lambda over 2 of the frequency we want, we have a mode over this edge. So in the typical patch antenna, we want just one mode. So usually we choose one of the edges. For example, I will say I will choose these two edges to be radiating. Means that I chose already that I have this thing like lambda guided over 2. Means that equal lambda over 2, but this lambda is divided by epsilon effective, which we learned how to calculate it. But we can generally start with the same epsilon we have because it's basically very close to the same value for the typical patch antennas. But generally, you can start from the value which you can find in the online calculator things. And then I will choose this dimension to be slightly less than L1. And there is ways actually that we can choose it to be even bigger if we want better matching, but we will have to be careful of the feeding location or something, which we'll talk about it soon. Yeah, so anyway, so this is the starting point. I prefer that I start by this lambda guided over 2 to calculate lambda guided. From the frequency we get lambda, and then we divide it by epsilon effective, which is the epsilon r which we use, and then we choose this width to be slightly less. Well, after we draw and create the model, we need to basically create the ports, like the feeding mechanism. So here in this example, I will choose to feed with coaxial feeding. This is useful for multi-layer antenna, how to integrate with modules, you know, with multi-layer structure or something. But then in other tutorials, I will show another feeding mechanism, even based on like your feedback or something. So for now, like we create the model, here is the parameter we use. I prefer everything to be very parameterized, and not to get lost, you can just put here the description of each parameters, you know. So for example, you can say, okay, this is, for example, ground size, for example. You can say this is patch, and then y, or you can say like this, length y, okay, and the same. It's just I prefer, for example, to do something like right first patch, and then when you sort it by order, like by the name, like I mean, like you can basically, if you write the parameters for everything starting with the same name or something, you can group the parameter together, and then if the circuit or the structure is big, you cannot get lost. And then, you know, for example, I can say ground, for example, elevation, right? And then we can say again, like, here it's not really case sensitive, but just as I said, for consistency, here we can say metal, or we can write just thickness metals. Okay, so it's like, you know, you try to make it easier for yourself. Okay, and then so now as we described it, like how to choose the parameters. So for example, I'd like also to make it parameterized. For example, if I say that f node, for example, the center frequency which I want of the patch antenna will be something 10 gig. Okay, and then here I write frequency in gigahertz, right? Okay, and then this lambda, let's say lambda node, right, to be something in millimeter, to be something 300 over f node, right? So this tells me like after just the calculations, how we calculate lambda from f, it is something like this, 300 over f naught, but and this wavelength and millimeter, right? So I start initially, I will choose y dimension to be the patch we want. So for example, I prefer that the ground will be like lambda free space over 2, right? And then for the y dimension, I will make it lambda over 2, but this is also, you can say, not divided by square root of epsilon substrate, right? The square root just straighten it like in MATLAB. Okay, so it's just square root like this. SQR, okay. And then I will choose the X dimension to be slightly less than LPY, and then press F7, or actually home, to modify. Okay, I just got used to press F7 and it works. Although they write here to press home. Okay. So here's then the patch antenna. And then you can also, for consistency, for yourself not to get lost, if you press on view and then dimension and then you do the patch like this, and the ground, you can literally, not to get lost, you can always know what is the dimensions you are using, not to be lost. I mean, if you press dimension and then you just come on the edge, you do like this, and then dimension, press on the edge to do like this, and then you can always hide them from here. And on dimension you can just do like this, and you can say hide all dimension, and then when you want to see them, show all dimensions, and then you show what are you doing. So I will do like this, hide all dimensions. Okay, so once now we do like this, we need basically to draw or create the ports. And here I will basically do the feeding mechanism by coaxial cable, coaxial waveguide or cable or something. It will be just vertical via or something. So I will do something like this. This is what I like to do it. I do like this. Okay, and then I choose different component, for example. Again, for consistency, it's up to you. Generally, you can say port, so collect everything about the port there. So I will start, for example, do like this, port via, okay, and then I'll choose center frequency of everything. For example, in my case, I'll XF, like X of the feeding, YF, and just for the pin itself, I will have 0 inner. It will just, I'll have some diameter. I will write like the radius or a d pin over 2. I just write in terms of the diameter of the pin, okay, but you are free generally. And here we go. I can say, for example, let's say, I know that you always feed the antenna, but you can always make it parameterized as you want. But here, just for, because I know what I'm doing, so say it's always go from the patch to something like from ground, like till the ground, but minus some L pin. It means this is the extra or the excess length beyond or below actually the elevation of the ground, right? And then when we do like this, we can set generally anything. For now I can say 0.2, x 0, y 0. This will be changed later, of course, and I will do like 1. Okay, and press OK. So what we did is that we created like pin like this, okay, and then to feed with this pin, it must be part of coaxial cable, right? I mean, this should be the pin of the coaxial cable or waveguide. So what we'll do is that, using again this thing, I will start by, for example, I'll write port body, for example, and then I will do like this, and then I'll say the out, or yeah, I'll write the out over 2, like the outer radius, and then the same center frequency, location, the same center of the pin, and then it goes from where? It goes from the ground, L ground minus L pin, right? And then, okay, the out, I would like to make it some percentage, like 3 multiplied by the pin. So we have something like this. So here we go. Like generally for the port, it has, now I just do it metal, okay? And this port generally will have something like, it should be like metal, dielectric, metal, right? So for now I do like this. So first thing I do is that for the port, I just copy the So you can do Control C. 1 second, so Control T. Okay, Control T, like transform, or you can just press here anyway. So I will write translate, copy, and everything is the same. It means that I just copy in the place, right? I will press OK. So this thing is, I will do something like change the material. I will make it new material. This new material, call it port filling. And then you can write epsilon port, right? And then again, I like to do like this and choose different color for ease of, like view for yourself, right? And this epsilon uses now something existing. I'll use 4, for example, and then I press OK. So now we have the filling, the cover, but still this solid thing. So I need this cover to be basically hollow. I mean, like this port generally I need to be hollow, right? So I would do like what? In the body itself, I do again Control T to do the translate, and then I will do scale, and then I make copy, and this scale will make it non-uniform. I don't want scale in the Z direction. I want just to scale in the X and Y. Okay, and for X, I want to add some thickness. I can show how. So for now, it is like I want to scale it something like to be the out plus 2 multiplied by TG over the out. It means that the old dimension is the out, and I want it to be extra by 2G, right? Like to add the thickness of the metal in both sides. And then I'll do the same in the Y dimension as well. And then before we click yes, we can just see what's going on. Yeah, so it's like we created another shape, just a bit bigger, right? And then do like this. Okay, and then now here we go. So now we have different things. So we can just need to subtract the body 2 from body 1, or body actually. So I can do like this. I can do press on minus sign, or you can say the Boolean thing here. You can say subtract. And then they say choose subtract from. Okay, so I will do like this, and then I'll press enter. Here we go. Okay, this is opposite. I will do Control Z. So I will do first choose the bigger one, and then press subtract, press on minus sign, and then press this body. I press enter. This, here we go. So we choose first the outer one, and then we press minus, subtract, and then we choose the second shape, and then we press enter, and then here we go. So this is one thing, right? So if we see here, like still the ground is also solid, like the via is not going through, right? So if this is the ground and this is the via, right, it does not go through. So what I do is, like, in the port body 1, right, like, which is basically the filling. Yeah, actually we can go to the main shape, and we let it just start a little bit from a little bit higher thing. So I will just start it from TG. This means that I want it to be just not from the lower edge of let me see, yeah, not to be from the lower edge here. I want it to start from here, and the reason is like this because I want to create a hole in the ground to let the via go through also, right? I will choose the patch antenna, like the ground itself. I'll press the slash, the right slash, which is basically like you divide or something, or you can do insert, and then you do choose the filling, and you press enter. As you can see that you created something like hole. So of course you could already create a piece of metal or cylinder and then you just subtract, but it is another way. I'm just interested to show you different ways of doing this. So this is the way I do it. And now we have the pin, we have it parameterized, and here we go. So remaining now that at the beginning, we will create here a port, and I'll explain later how it will work. And then after we create the port, we choose the way of the feeding, you know, like let's say the location itself. Okay, so to choose the port, I will, let's say, press 1, press space to fit, to zoom fit. Okay, like if I go here somewhere and press space, I go back 1, it aligned to the closest view, right? I mean, if I do like this, and press 1, it goes to the closest view. And then if I do like this, I'll press 1, it aligns it to the closest view as well. So okay, I come here, I press F to choose the face, or no, remember, like maybe in the picks, I do pick face. Okay, so I press on the outer conductor. So, and then in the simulation window, I do waveguide port. Okay, waveguide port by default, to open you this window, it basically create the port around the edge, like let's say on the boundaries of the shape or the face you select, right? So it covered all of this area, and you have the chance to increase it by whatever any dimensions in each side, like, you know, but here in my case I will not. Okay, and then we can, of course, there is here a number of modes and define like integration line for the impedance and shielding and so on. This is all I can talk about it in the whiteboard, I mean, but for now I will do like this. So like I have a port, and then we can just choose for now any location of the feeding. For example, let's say it is already referred to the center, so I like to say like this, LPY over 4, for example. Like I shift to the middle of the distance to the edge, right? And then press F7. I can do it in this way, right? Let me see. Yeah, let's see. Press it. No, press Z. Back it again. Sorry. And then seems like the patch itself or the pin itself is not really moving. It means that I forgot to do this way. Yeah, it sounds like the scaling thing. Yeah, I mean, I think I catch it. So the scaling thing, if you do a history list, okay, we scaled in some here. Yeah, so here we go. Like we can, this is the way how we edit. We go exactly to before this thing, right? And then the scaling of the port body, I will delete it. Okay. And then we'll run to this thing, okay? And then the port body, I'll Control T, and then I will scale it first. I have to write it in the ship center. So I will guarantee that it is scaled, but exactly in the same location. So we can do the out again, plus to like TG. Okay, over the out, and then we do here the same, and then copy, and then view, and then this is fine. And then here we go to the history again, and we want to run the whole way, and then we press close. So here we go, it is fixed. And then we can actually move anything. If we want to move it a bigger distance, and move all the way. So here the mistake is like when you want to copy, you have to choose it to be copied to the same location, you know, and then sorry, like to the center shapes, and then when you move the center of the shape itself, the original one, everything will move with the same direction, the same amount, the same direction. So press 1, and then okay, I'll rotate here like this, whatever, and then press 1 again, and then go like this, press 1 again. So here we go. And then to just do the setup for final thing is that when we do here in the setup, for now, I mean, like we're not going much details about this, and just one port for now, and I'll let it with the general things and everything as it is for now, okay? And then we press start, and then we can see the result, and then we can discuss. Great. Given that the simulation is done, we can just quickly check it, and we can basically see some features. I mean, like I just want to discuss some features, and then we'll go to the whiteboard to explain and to see how to tweak the design or something. So anyway, so we'll check here in the section, we can check these parameters. So we know, for example, that there is some matching, like there's, you know, like there's some performance around 10 gig, which is the desired frequency, which you want to do. And clearly it's not perfectly matched or something. And then we can also see, like, if it's not matched, there's two things. There is the port of which we are feeding, like the coaxial, and there is also the impedance of the antenna itself, right? So, okay, for the reference impedance, we see the impedance of our port, like the source, and then it is not already 50 ohms, so we are now trying to match to this value, like something like 32.5. And yeah, and then for the port, we can see in the 2D results here, we can see in the port modes, you can press port 1, we just press on the E field or something, we can see something like this. We can see what's happening in the port is like TEM mode, and the line impedance is 32, the wave impedance is 188. So the line impedance, it is like they integrate between this conductor to this conductor to see what is the impedance in terms of like the circuit, you know. And the wave impedance, it is like just the speed of the wave, like this parameter which is related to the treating the TEM wave as a wave. And this is the wave impedance, which is basically connected to the material, and it is connected to the wave, to beta actually, you know. And yeah, other things we can discuss later if we have some issue. Okay, so now we know that this impedance here, it is the same what we find here, okay? And then to see what is happening in the antenna itself, okay, so we go to the Z parameters. We can see that we can check overall the magnitude of the impedance, Z11, and we can check the imaginary, we can check the real. Before this, if this thing does not show in your place, we can, from the post-processing, from the S parameters, you can choose always calculate Z and Y and the voltage standing wave ratio. But anyway, so what this Z parameters actually tell us, you know, it tells us that there is the resonance, the actual resonance of the antenna itself is around 9 gig. It's not really 10. And the reason is that the epsilon effective, which we calculated, is not purely right. We calculated based on the epsilon, which we have, which is slightly higher than the other epsilon. So we should correct this to have the resonance here. And it tells us also, and this we can check actually from the imaginary part. Imaginary part means that there is resonance around this frequency. And the real part, it tells us what is the impedance I'm trying to match to. So having the real and imaginary part, okay, it tells us that, for example, that now in this frequency around the 10 gig, it is the imaginary part is around 0, and the real part is closer to 32 or something like this, and that's what's a bit closer to the matching. And then at the actual resonance of the antenna, we don't really have nice matching. So we can go to the whiteboard to explain a little bit, and I will actually share some tricks on how to quickly adjusting this matching on the desired frequency, and at the same time to also see, for example, if this bandwidth is the maximum or we can get better or something without any additional circuits or something. Well, we are finished. We are done with the simulation, and now it's time to study these things. So when we go to the whiteboard here, so here what we have for now is like, this is our matching, this is our impedance, this is our reactive part, and then we just want to see now what is happening in terms of the impedance, like how we match, okay? So first of all, like, we should know that this reactive part is deciding with the resonance. This real part, it is deciding what's the input of the antenna, like seen from the port. And we have still the parameter of choosing the source impedance itself. And here's the result, like it shows here, this is the point of closest to the matching. It means that the imaginary part is closest to 0. And at the same moment, the point of the real part is closest to the source impedance, right? And then, okay, so how we choose the location, right? So start by actually deciding what is the mode which is happening there. Okay, so we know well that the patch radiating like this, right? If we look at cross section, okay, and then we have that here two opposite things. Okay, it means that they cancel each other. And then it means that if we look at the E pattern, it will be something like this: maximum, 0, maximum from the other side, like positive maximum, 0, negative maximum. And for H, it will be here 0, and then maximum and minimum. Means like what? If we do the surface equivalence and we have here a current, so this current definitely should be 0 in both ends because it's an open circuit, and maximum here in the middle, which is this H. And we know that H is proportional to the current, right? And the same moment, the voltage is proportional to the E, right? And then E is proportional to the voltage, right? So we know that the electric field is like this, and the magnetic field is like this. So it is like we can expect that here, if we do the impedance, input impedance equal V over I, it means that here V is minimum, like 0, right? And then we have here the input is equal 0, and there is opposite, I equal 0, and then the input equal infinity. It means that we have two values as we sweep from here to here. We can get from 0 to infinity. And also you can look at it in a different way, honestly, like if you have here the ground and here is the feeding which you feed, and then if you use the transmission line model, we have two impedance in parallel, like short stop here and long stop. So if we are feeding here in the middle, we have lambda over 4, and here's an open circuit. It's transformed like short circuit. So we have here Z input equals 0. And the same, if we are here, we can have actually directly infinity, right? So this is the point. So we have to sweep generally between here and here. And from the simulation, we will see that what only will happen is that this peak will go less and higher based on the location. Here is go less as close as we can. It goes less and wide if we come closer to the center, and it got far high and narrow if we go far. It means that it depends on the port impedance to decide what is the bandwidth we are getting in terms of like the line width, and also the dip itself. Like if we look at the matching, like the dip can be like this or like this. It depends on where we are doing. Okay, so I can show it more, but the only difference is that in the cavities, like when you introduce like via or something, it changes a little bit. And the cavity itself, like the existence of the via itself, it is something. It changed the size of the cavity or something. So we are expecting as well that you will see something like a little bit shift in the peak. Like it's not big, I guess, but usually as we will see in the simulations anyway. So we'll see like the major thing will happen is this peak, and little like minor change in the center frequency. This is one thing. Okay, so this is one thing, how to fix this edge, like how to fix this to be more matched, right? So how we shift this frequency. So the easy way for this is that I know now this is the resultant, like this is the actual resonance, right, happening here, right? And I want to shift it here, right? So it is simple, like I can do just the frequency or the dimension scaling. So we have, for example, L1, it have resonance at 9 gag, for example. I have L2, I want it to have resonance at 10. So the scaling is in the same ratio, for example. So we can say L2 over L1 equal, let me see, like if I want L2, it should be smaller, right? So it would be 9 over 10. It means like if I want shift frequency to be higher, so the dimension should be smaller. And that's why, I mean, like, just not to confuse it, I mean, like L1 prime and then L1 prime means that I can just change the dimension a little bit by the same ratio, and I try to sweep the impedance, the port location to get the right impedance level. And the last thing is how to adjust the source impedance itself. I mean, so we feed by coaxial, this thing, and this is the inner conductor, this is the outer one, okay, and we have epsilon like this. So any transmission line is like this. Everything is connected to the capacitance. Like if you know the capacitance, then you know Z node, whatever L or something. So it is basically, we get it like it is basically determined more by the ratios of the diameter. So if this is the N, the out, you'll see like from any online calculator that, and of course the epsilon as well. So it usually depends on the ratio. So it does not matter about what is the size of the pin, but it just the ratio. So we will adjust the ratios from any online calculator based on epsilon we are choosing, like 4. We'll adjust the ratios to have the 50 ohm again, and then we will and then we have the source impedance equal 50 ohm, and then we have to adjust the port location itself to be in the same, to choose also the corresponding 50 ohm here. So let's see how we do it in the simulation. Well, back to the simulation again. So the first step is to basically adjust the input impedance itself of the source. And for this reason, we go to the whiteboard, I mean, in the online calculator. So for example, this is the current dimensions we have, like 0.3 outer conductor, 0.1 inner conductor, and here is the epsilon. We give, of course, the formulas and so on like this, but as we said, it is just inversely proportional to the impedance, sorry, to the capacitance. So it is like if we want like Z and C is like equal like this. So if I want to increase it. So I want the capacitance to be less. It means that I want the spacing to be more. The spacing, it means that I want this one to be a bit little bigger. And then I can do like this. If I adjust it by this dimension, 0.53. So now we have the 50 ohms. So we can just double check very quickly. So in the parameters here, parameter list, an outer conductor is yeah, just here I have the ratio like 3, but the other one, because just it is depending only on the ratio, because I have the ratio here like 3, and that's why give me the same number which I have. But I will do just like this, 0.1, make it a little bit smaller. Or actually I will do something, you know, like to just be sure that this theory is correct. So I will do something like this. 0.52 divided by 0.1. This is the same ratio, but on the new dimensions, because I have here the diameter of the pin will be something smaller. So I can see now that the port impedance will be 50 ohm instead of this. And then let's wait to see what would happen. We're expecting that this Z reference will be very close to the actual value, which is 50 ohm. Okay. Here we go. Like we have the scaled more. Like, of course, it's not 100% like the online calculator, but it's very close, and similarities like this. So then you know how it will change. So you can just start to play with the dimension. Like, you know that if you have to decrease or increase it. But anyway, these things should not make any difference in the matching of the antenna. I mean, like, at least so anyway. So we can double check again the result. We can see a little bit better matching because we are increasing the input impedance. But if we look at, for example, the real part and imaginary part, okay, what is it? Oh yeah, not the Z the Z part, the Z parameter. So here we can see that little bit shifting of the resonances. Why? Because we changed the cavity itself. You know, like for example, if we have this as a cavity, it's now we increased the opening, right? And increasing the openings makes the cavity looks, you know, like somehow smaller, you know, and that's why resonances comes a bit, you know, like to the higher frequencies a little bit. But this what we are saying is like everything is different a little bit than the analysis, because when you modify the ports, it already contribute to the device itself, right? It changes the parameters, like changes the it do a perturbation to the antenna, right? So based on this, we want to shift this peak, this, let's say, crossing, this resonance here to the 10 gig. So we do like what? We see here frequency is 9.3, here is 10. So the first thing is like I can go to the LPY, this thing. I can say, okay, I want to scale it down by 9.3 over 10, right? To shift the frequency a little bit. And then press F7 to modify it, and then like the patch is a bit smaller. So we're expecting that it will be more to the higher frequency, and let's see what we get. Well, simulation is done, so we can look at the Z parameters. We can see the shifting almost from the same number, because, you know, I just multiplied, you know, not accurate. I just write 9.3 to 10, but it brings me the resonance something like very close anyway. So it's like it is linearly proportional. And then the Z parameter and the S parameter, let's just have a look at the matching. You see it's like literally we shifted only with the same percentage we want. And real part should not change a lot or something, but you know, it depends. Like as I said before, that generally when the numbers are so big like this, it is really sensitive to anything in the patch. So for example, when we change the patch size, it means that the hole which we have before here, relatively it is not the same. You know, for example, let's say if this hole is 0.1 of this patch, so I shrink it the patch, but the hole is the same, right? So it is like, it is not exactly scaling down. It's like I'm scaling down the antenna, but the perturbation is bigger. And that's why the thing here, we cannot say that, you know, like we just changed one thing, we changed two things, right? So anyway, so we are like this, and then we're expecting, if we are sweeping the antenna, feeding location itself, this one, among between 0 and the edge, we can find the point where we have good matching. So how we do it? First, I mean, I will just delete the results to have the traces here not existing. And this is, I just saved it to have a screenshots from it. I will just delete. Okay, so now we should do parametric sweep just once to just understand well what's happening and also to go through it. So the way I like to do it is that I define some parameter. I call it, for example, sweep. Okay, and this sweep some dimensionless parameter I choose, and I'll play with the feeding, right? So I want the feeding something like fraction of LPY over 2. Right, I want to sweep around the edge, like around all of, like the half of the length. So this parameter can range from 0 to 1. Means that I want to change all. So it's like I would just multiply this a little bit by 0.9 or something. The reason is, you know, like the reason is that when I do like this, because I don't want in some situation that the pin, it goes half of it inside and half of it outside. So for example, if I do like this, and then if I do like, I have this sweeping parameter. So if I do zeros like this, if I do 1, it go to the, it go to the edge, right? It go to the edge of the port. So if I don't have, if I have this actually like 1, as you can see, like it will go like that, it will just bother the meshing. So you can of course calculate it very accurately, but as I said, it's up to you guys. So just like this. So now I want to sweep this sweep parameter from 0 to 1. And of course, you see the other results. So I will go to the parametric sweep. I will get new sequence and new parameter. I will choose this parameter sweep, and I will sweep now for linear. I sweep from let's say 1, okay, from 0 to 1. Just 0 is not really useful, I know, but we can take with the step of 0.1. Okay, and then press OK and press start, and let's see what will happen. After it finish, we will back to see the results. Well, after the simulation is done, we can see for now that we swept over the location. So for example, we can see that it goes from no matching at the center of the patch, and then start to get to raise, and then you get some matching here, and then here's also matched in the blue one, and then it goes mismatched again, and then start to decrease and so on until it is almost not matched, or this is similar or basically closer to the result which we got before. So the first observation we need to see that when we look at the real part here, what we see, right? We see that we start from 0 with no match, no coupling to the mode actually. And then the impedance start to get higher and higher and higher and so on. And when it gets higher, shift a little bit to the low frequency also. And the reason is, as we discussed before, that the existence of the via itself somewhere in the patch, it's not always the same. Like the contribution when it is in the edge is different than the contribution when it is inside and so on. Okay, so it depends. Like if the place where the via is if this basically region have like a high field, so the perturbation is higher, and vice versa as well. So this is one thing, and we can see from the measured part that we also have the shifting. So we can see that it is not, like exactly, maybe the matching, it's not exactly happening in the same location of the imaginary part and so on, because actually it is like, we have to guarantee at the same exactly frequency we have both of the real part and the imaginary part, like the real part very close to the port matching, like the port impedance, which is the 50 ohm, and the imaginary part is the lowest, right? So, and here we, for example, so now we understand that we can get something between 0.2 and 0.3 and 0.4. So I will go with 0.3 for now. And then we can see that the last parameter we can change is the width of the patch, and it decides somehow also the impedance, or it actually decides also the parasitics, So the location, it gives you, if we fix the patch width, what's the best place to feed. And then when we reach this location, we can optimize together with the location around, the feeding around in the y-axis. At the same moment, also the width of the antenna, giving that the other considerations in the design or something. So for now, I can fix this sweeping and up to 0.3. And then let's see if we have the result we want or not yet. Let me again delete the result here. And then here we go. And let's see what we'll get. And then we'll study the last thing of the width of the patch. And then we'll be done with the first tutorial. And after the simulation is done, we can see that we have the matching here, right? And the 10.3 gig. And if we look actually on this frequency, what exactly we are getting like real part is very close to the 50, and the imaginary part is close also to the 0, right? So ideally, if things are like ideal without this perturbation thing of the via or something, this should be, the crossing happens around this frequency, like let's say this dispersion thing. This point should be down here at 0, but this thing, it means that the impedance seen is not purely, let's say, real at this frequency, and sometimes we cannot really couple the low reactive part with the imaginary with the real part at the same moment, and here it comes the role of the width of the antenna. So for example, here we can see that the antenna is more like inductive, right? Because most of it is to the positive values. So if we just decrease the patch, like if we increase the width of the patch, we can actually improve the matching a little bit more. So if I say, for example, get 0.9, and then let's see what we'll get here, 7, and then press start, and just let's see, do a quick comparison, and then this will be the last thing. Well, simulation is done, so we can look at the result. What happens is that the bandwidth is bigger, matching is better, And the reason is like for the imaginary part, we can see that the peak is more down, like, you know, the impedance of the transmission line or the patch is less because the width is bigger. And the dispersion also is more wide in terms of the slope is less and the variations of it is less. So we are expecting that if we increase it more, we can play with extra degree of freedom. And of course, we shift a little bit the center point to the low frequency or something. And so it is like it is more close to the 0, for example. So we are expecting better matching here in terms of the depth of the matching. But anyway, like all is the same. So the last thing, of course, because it will not be like something very analytical or something. So the last steps that if you want to do this step to here, so it's like you have to do the last frequency scaling. So this is why I'm saying that I like to link everything in the same way. That because everything is depending on the relative distance and the relative location and the relative dimensions. The only thing is it can really make it different that the feeding mechanism, I don't scale the ports with it. Like, so, you know, for example, if I scale everything, I don't scale the ports. And usually you don't if you do any antenna or something, because the feeding mechanism is the same. Like, for example, if you have a via or something, you cannot use different thing. You know, I cannot really scale it to very big or very small or something. That's why it needs always a little bit some tuning. So here, the last thing, we know that the patch needs to be a bit bigger with this ratio, right? Between like 10.27 over 10. So I can say, I know that I want it to be bigger, right? So I will say, I want multiply by this. Yeah, and we are expecting finally it will be aligned. So let's see what will happen. Okay, once it's done, let's see what we get. Okay, let's check the result. Here we go. Like, as we just said, like just linearly proportional. So I just changed a little bit this dimension, and all things are connected, right? So it's like I tune basically everything in terms of the antenna itself, like the length, which is the resonance, and also the location of the feeding, which is basically connected to the dimension as a, you know, as like relative distance or relative location or something, and even the width, right? So now we know how to design. So it is like, to summarize, we start by close numbers, very estimate or rough estimate numbers, which we get it from the analytical things, and then we do the simulation once, and then we choose the location of the feeding based on the impedance level, and then we start to tune a bit in the width and to see if it could get better. And anything we get, we don't have to hit this. The most important that we get this dip somewhere, right? So if we get this dip even somewhere, we can start to scale everything. So it's like when we scale everything, we get the same result back to our frequency, and then we can tune a little bit more or something. So I think now things are clear in terms of how to design the antenna. So in the next videos, I will explain if I have some antenna, what I should do to scale it to another frequency. So if you copy antenna design from a paper or something, how you can scale it very fast to your own frequency, giving that the substrate effects and so on. And I will do further analysis on how to understand the results, you know. So basically we'll be answering two questions: how I can be sure that this bandwidth which I get is maximum, or what bandwidth I should expect from the antenna, and how I can scale it to higher frequencies. And then if I scale it to higher frequencies, what is the bandwidth I should really get? So this will be the topic of the second tutorial. Thank you.